Okay, so hello. So here we're going to talk about the concepts for problems 4, 5, 6, and 7. Of course, the way you'll really learn this is by solving these problems. But we're going to give an overview of the concepts that you'll need. Okay, so first question, what is a linear combination? Okay, well, I always start with an example. So here's an example. This is a linear combination of four vectors in R3. So each of the four vectors is in R3, like this is in R3. I've written it as a column here, but we could write it as a list of three numbers separated by commas. And we'd say that's an element of R3, so we call it a vector. Now, in front of that vector is a number, in this case pi. In this case, it's a 5. Well, actually, here it's a negative pi is in front of it. And those are scalars. We call those of 4. So let's say a linear combination of 4 vectors in R3 is a sum, or is a weighted sum. Add the vectors after scaling them by real numbers. So each vector gets a real number, and it gets scaled by that real number. So here by negative pi, and then added to this vector, which is scaled by 5, then added to this vector, which is scaled by negative 3, which is then added to this vector, which is scaled by 2. And so if we do this, if I'm actually going to compute this, the result will be a vector. So after I do all these scalings and additions, I again get a vector. So the question is, what vector do I get? Well, here I get 2, 4, 0. Here I get 0, positive 3, minus 6. Here I get 5, 5, 5. Here I get minus 6 pi, 0, 0. I turned all these into pluses, even though there was a couple minuses. I sort of absorbed them in. Now I just add up the components. So in the first component, I have 7 minus 6 pi. I can't really simplify that any further. The second component, I'll have 4 plus 3 is 7. 7 plus 5 is 12, so I have a 12. And then the last component, I have 0 minus 6, 5 and 0, so I get negative 1. So this is a vector. It lives in R3, and it's the result of this linear combination. But the linear combination itself is this expression here, where we're scaling and adding vectors. Okay. What is the next question? What is the convex whole? What is a convex combination? Okay, so first some examples. So here I have 3 points in the plane. Their convex whole is the entire triangle, including everything inside of it, and including those points, which are the vertices of the triangle. So that is the convex whole. So this, I would say this is the convex whole of 3 points in the plane. Okay, what if I take 4 points? Well, here, let's give them some more visual. So I'm going to take this point, maybe I take this point, maybe I take this point, and maybe I take this point. So their convex whole is going to be some object. It's actually a 3-dimensional object. It's like a tetrahedron. Maybe I can draw it better like that. So the 4 points were the vertices, and the convex whole is the tetrahedron. So convex whole is like in the plane, it's like if you took a rubber band and shrunk it, and you kept those points fixed, then the rubber band would shrink to find the convex hole. So intuitively, that's what it is. Now, what is it precisely? So what is the convex hole? Well, the convex hole of a list of points, or a list of vectors or points, is the set of all possible convex combinations. Convex combinations of those vectors. Okay, so what is a convex combination? So this point here is in the triangle, so this should be a convex combination. In fact, if I take, so right there, that point is a convex combination, so I'll show you what it is. Let's call this P1, P2, P3. Then that point in the center is a linear combination, but it's special because the coefficients add up to 1. So P2 is also in the convex hole because P2 is equal to 0 times P1 plus 1 times P2 plus 0 times P3. And the coefficients add up to 1. So remember when you're if you're weighting, taking a weighted sum or averaging something, the coefficients have to sum to 1. It's like you're mixing those things together. But you're only allowed to use one. In probability theory, all the probabilities add up to 1. And so the probabilities are numbers and they have to sum to 1. So that's sort of the same idea here. Let's take this point here. It's sort of halfway between P2 and P3. And let's write it as a convex combination. I'm claiming that it's 0 times P1 plus 1/2 of P2 plus 1/2 of P3. And again, the coefficients add up to 1. This 1/2, 1/2, and 0 add up to 1. So what is precisely the case is that a convex combination, convex comb for short, is a linear combination. A linear combination whose coefficients, which is just another word for scalars, sum to 1. Okay, there we go. Now, what is the dot product? Okay, so that was the end of convex hole, that was the end of convex combination. Maybe one more thing, what I could say is that I have CIs times VIs, where each VI is a vector, let's say in R3 or just any, it can be on R2 or R1, and each CI is a real number, where the sum of the CIs is 1. So this is sort of symbols and words for the idea expressed up here that a convex combination is a special linear combination. It's a linear combination where the coefficient numbers add up to 1. So over here, 2 minus 3 plus 5 minus pi is not 1. I don't know what it is. 7 minus 3 is 4. 4 minus pi. Oh, actually, it's close. It's close to 1, but it's not 1. So this linear combination is not a convex combination. Okay. And remember, this sigma symbol here is just a shorthand. It's because it's tiring to write out C1 v1 plus C2 times the vector v2 plus the scalar C3 times the vector v3 plus the real number C4 times the vector v4. So if this was a sum of 4 vectors, sometimes people put a 4 up there to say, yeah, this is a sum, sigma for sum. Sigma is this symbol here. Sigma for sum of some number of terms, and in this case there were 4 terms. So this is a term, 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 term. the word term is something that we're adding together. In this case, each term has two factors. The word factor is something that we're multiplying together. So we're multiplying the real number and the vector together, and so we'd call them factors. Okay. That was a little aside on this symbols. Let's do the next one. What is the dot product? What is the dot product? So here I have a vector in R3 and another vector in R3, and I'm dotting them. The dot product. So what do? I take 2 times minus 1, and I add 3 times 2, and I add 0 times 5. Okay, so what do I get? This is 4. So the dot product of these two vectors is 4, which, by the way, is a real number. So we had a vector in R3 and a vector in R3, and they dotted to give a real number. Let's do this one. It's 3 times minus 1 plus 2 times 1. So 3 times minus 1 plus 2 times 1 equals minus 3 plus 2 equals minus 1. That is a real number. So we had, two vectors. This time they were in the plane, and we dotted them together and got minus 1. Here we do 5 times 5 is 25. So now I'm over here. I have a vector in R3, a vector in R3, and I'm dotting them together. What do? I add up some things. So 2 times 2 is 4. Minus 3 times minus 3 is 9. Oh, in fact, this is the same vector dotted with itself. When it's a vector dotted with itself, I ended up just summing the squares. 5 squared is 25. 2 squared is 4. Minus 3 squared is 9. So I have to add this together, 38. That's a real number. So in general, if you have v dot w, the answer will be a real number, even if v is in Rn and w is in Rn. So the dot product, this dot, it eats two vectors and spits out a real number. Now, I want to pause for a moment, and there are different symbols for this. So if I'm doing the dot product of v and w, of vectors v and w in, let's say, Rn, then the symbol I use could be, and there are several options. So here's one symbol, v big dot w. Here's a different one, v and then an angle bracket, line w angle bracket. This is used in physics a lot, especially quantum mechanics. Some other ones in math, sometimes they put a comma, v dot w, and then put it in angle brackets. What else? I mean, in Julia programming language, you can say dot, and then open a parentheses, and then v comma w, and then close the parentheses. Because really, the dot product is a map from the space of vectors cross itself to the real numbers, meaning it eats a vector and another vector. It needs two vectors, and it spits out a real number. And this real number is the dot product. Okay, so now I've shown examples of dot product. I've shown you symbols for the dot product, but what is the dot product? So finally, what is the dot product? Here's my answer. The dot product of v and w is the sum of products of their corresponding components. So in symbols, we'd write vi, wi, the sum from I equals 1 to n. I mean, literally it's v1, w1 plus v2, w2 plus. I mean, here I'm saying that I'm thinking in my head V is V1, V2, V3. Let's say if V and W are in R3, then they have 3 components. And then the dot product would be like that. So this is the dot product. It is a sum of products where you just multiply the entry and add, multiply the entry and add all those up. And that's the dot product. So I mean, let's go back to the example. I don't know what that was. What does that do? So this example here, that's why we got a -2 was from 2 and -1. A 6 was from 3 and 2. And a 0 was from 0 times 5. Then we added them up and we got 4. And that's the dot product. Okay. 2 more things. Here's our next question. How does the dot product relate to lengths and angles? Okay, so right here, V is 1, 2. Do you see that that's V? It's 1, 2 in my drawing. Oh, I didn't have a W. I have an A. A is another vector. It's 4, 1. There's A. B is another vector. It looks like it's -2. No. It looks like it's 2, -2. And C is twice as long as B. It's 4, -4. Now, V dot A is four plus 2. Okay, that was easy. Let's do V dot B. V dot B is 2 plus -4. 2 plus -4 is -2. Okay, and let's do V dot C is 4 plus -8. Okay, so what we're seeing here is that notice V and A. V and A have a positive dot product. And V and A are pointing in roughly the same direction compared to V and B, which, like if I draw on this line, you can see B is sort of going at least in that direction rather than this direction. And so V and B are sort of pointing away from each other, so we get a negative number. Now V and C is twice as long as B, and so we get twice that negative number. And again, you can see that C, C over here is pointing more this way than that way. And so back to our question. How does the dot product relate to lengths and angles? So it turns out, and this is this is a theorem, which means it's sort of surprising discovery. V dot W is equal to the length of V times the length of W times the cosine of the angle between them. And this follows from the law of cosines, which you have seen in trigonometry or geometry, but it's actually not that important for us. What's really important is that we just know this fact, and we're going to use this fact often. So now, what are these things? So I have to tell you what these are. So theta is the angle between V and W. Okay? Now what is this? This looks like absolute value notation. Well, what it means is it's a symbol. It's like the size of V or really we call it the length of V. So what is the length of V? Well, the length of V is defined to be the square root of V dot V. So we take V, we dot product with itself, and then we take the square root, and that is the length of V. And this actually follows from the Pythagorean theorem. But let me just first say what this is. I mean, what's V dot V? V dot V is V1 times V1 plus V2 times V2 plus, so I can just do like this. Let's say that V is, if V is in R3, then V has 1, 2, 3 components. If V was in R4, then we'd have to do that. Yeah, let's make V be in R4. Then this would be the case. So the length of a four-dimensional vector is the sum of squares of its components. This is the definition of length of a vector, even in 4 dimensions. We could do 18 dimensions. This is going to be the sum of squares, square root. Okay, and well, then there's this one, but that's just the length of W, is length of W, which again is, I mean, obviously it's just the square root of the sum of squares of components of the vector W. So this is the same as that, is the same as that. And just to show you again in our example, remember up here where we did a vector dot itself, dot product with itself? Well, then we did 5 times 5 plus 2 times 2 plus -3 times -3. And so this is the sum of squares of the components. Here's the square of the component 5, the square of the component 2, the square of the component, and we sum them. That's the dot product. Now we've taken all these squares, so to get the length, we take the square root. How does the dot product relate to lengths and angles? This is the answer. How does the dot product allow us to